Welcome to all of you. Today we discuss Group C Basic Algebra DSCC-2 2024 Semester 2 under CCF Mathematics Honors, University of Calcutta. Question 5a. If A not equal to B not equal to C, find the rank of the matrix 1 1 1 A B C A square B square C square, where A B C are real numbers. The given matrix is a Van der Monte matrix, and let A equal to this matrix, then determinant A equal to B minus A, C minus A, C minus B. The problem states that A not equal to B not equal to C, so they are all real, distinct real numbers. So obviously determinant A not equal to 0, and hence rank of the matrix is 3. Now 4 by 4 Van der Monte determinant matrix with the element ABC, and the corresponding determinant, actually this is the matrix sign, not determinant sign. This is the matrix. Next question 5c. Find the value values of k for which the following system of equations has non-trivial solutions. And this system x plus y plus z equal to kx, x plus y plus z equal to ky, x plus y plus z equal to kz. Rearranging the term, first we this from this 1 minus k bracket into x plus y plus z equal to 0. Transform this kx into the left hand side, transform the ky into the left hand side, and transform the kz in the left hand side. So the right hand side are all 0. Actually, this is the homogeneous system. For this homogeneous system, the trivial solution is the obvious solution. So we are interested for non-trivial solution. So we find the corresponding coefficient determinant of the coefficient matrix. So this A is the coefficient matrix, and corresponding determinant is this k square minus k square bracket k minus 3. So determinant for non-trivial solution, determinant A equal to 0. So we get either k equal to 0 or k equal to 3. Values of k for which the system of equations has a non-trivial solution k equal to 0 and k equal to 3. If k equal to 0, extra is if k equal to 0, put here. So put the given system k equal to 0. So x plus y plus z equal to 0, x plus y plus z equal to 0, x plus y plus z equal to 0. Same equations. So we get only single equation x plus y plus z equal to 0. If we put z equal to t and y equal to s for some real s and t, so x equal to minus s minus t. So non-trivial solutions are of the form minus s minus t comma s comma t. Put s equal to 1 and t equal to 1. So get this x equal to minus 2, y equal to 1, z equal to 1. Non-trivial solution for this system. For this equation, only single equation here for k equal to 0. And for k equal to 3, put here k equal to 3, this k equal to 3. So we get minus 2x plus y plus z equal to 0. And after simplification, we get this x equal to y equal to z. So solutions are of the form t comma t comma t for any non-zero real number t. Actually, t for 0 is trivial solution, so we are interested for non-trivial solution. So t is non-zero real number t. Next question 6a. Using pivoting row reduced algorithm, reduce the following matrix to its row equivalent form. So given matrix is this. Now we first column has 0 position. This is the 0. So first we interchange second row and first row. Then we interchange this. So 4 4 8 0 and 0 2 4 2 2, and third row and fourth row are unchanged. Next we make the leading entry in the first row must be 1. So we divide first row by 4. So first operation R1, this transforms by R1 by 4. So first row divide first row by all elements of the first row divide by 4. So we get 1 1 1 2 0. Next for this leading one, for the first column, for this leading one, the other entries of the first column must be 0. So this 8 must be 0 and 6 must be 0. So we next operation R3, this new R3 equal to the old R3 minus 8 R1 first row, 8 R1, and R4 this the old R4 minus 6 R1 old R1 first row. So we get all elements below the leading one in the first column are all zeros. Next, for the second row, these two we want to one leading one for this element 2, for this one 2. So we divide the elements of in the second row by 2. So R2 equal to 1 by R2 old R2. This new R2 is equal to 1 by 2 old R2. So we get this matrix, divide the second row, this 1 0 1 2 1 1. Now we eliminate the entries below this pivotal element 1 for this second column. Pivotal element this second column, this is the first column. The pivotal element 1 is the first column, and pivotal element 1 this second column. And below below the elements below the pivotal element 1 are 0 0. So we have the operation R3, new R3 equal to old R3 plus 6 old R2, and new R4 equal to old R4 plus 3 into old R2. So we get this new matrix is this 0 0 4 0 8 and 0 0 2 0 4. Now next, first non-zero entry in the third row is 4. Therefore, so we make this pivotal element equal to 1 by dividing the third row by 4. So new R3 equal to 1 by 4 old R3. So this element is 1 here. This element 1, and correspondingly this element is 2. To eliminate the entry below this pivotal element 1, this 0. To get 0 in this position, we perform the following operation. This is the new R4 equal to old R4 minus 2 into old R3. So we get this matrix, and this is the leading one first column. This is the leading one pivotal element. This leading one for the second column. For the third column, this leading one is this, and 0 rows this after non-zero rows first becomes first, and then after the 0 rows, this is the row reduced echelon matrix. Now this is the problem is this row reduced echelon matrix this. So, and this is the row reduced echelon matrix is this. Next question 6b, consider the system of equation is this. Check the solvability of the equations by applying the row reduced echelon form of the coefficient matrix. Now we have the given system is this corresponding augmented matrix, and this is the coefficient matrix, and the constant terms this right hand column is this 1 minus 1 2. Reduce the matrix to row reduced echelon form. So first we this for this leading one, this eliminate the entries below the first leading one. So -3 to 0 in this position and 0 in this position 2. So if first we operate this R2 equal to R2 plus 3 R1, and the right hand side is the old value of rows and the left hand side is the new value of the rows, second rows, and R3 equal to new R3 equal to old R3 minus 2 new R, sorry, old R1, and we get this 1 0 0 first column, and for the second row, this is the minus point in this position is the in the 2 2 position is minus 15. So second row divide by minus 15, and third row by R2 by 15, and R3 by 1 by 3, R3 1 by 3, R3 1 by 3. Just reduce this. So this position is 1, and next we eliminate this 4 position. We want to get 0 this in this position 4, and so this operation R3 equal to R3 minus 4 R2, and this position is 0, and for this 2 we want to make this position 1. So by dividing by 2 third row, so R3 equal to 1 by 2 R3. So we get this, and this matrix is row reduced Euclidean form. Clearly, the number of non-zero rows in the row reduced Euclidean matrix, number of non-zero rows is 3, and also the corresponding augmented matrix is 3. So rank of A equal to rank of the augmented matrix is equal to 3. Hence, the system has unique solution. And after using the back substitution, we can easily get the solution of this system. Now, this is the basic knowledge for non-homogeneous system. For the non-homogeneous system, Ax equal to B, where A is an m by n matrix. M is the number of rows, n is the number of columns, and this is the n is the number of variables in the system. This non-homogeneous system, because B not identical equal to the null matrix. The system have 3 cases. Inconsistent system, that is no solution for this system. If rank A not equal to the rank of augmented matrix, then the system is inconsistent and has no solution. Option 2, the consistent system with unique solution. If rank A equal to rank AB, rank A coefficient matrix rank of the coefficient matrix equal to rank of the augmented matrix equal to the n is the number of variables, then the system is consistent and has unique solution. Case 3, system with infinitely many solutions. If rank A equal to rank AB less than n, then system is consistent and has infinitely many solutions. And for the case of homogeneous system, Ax equal to null matrix, where A is m by n matrix, the system is always consistent, because this is the 0 solution, that is the x equal to null matrix, that is the trivial solution. We have always this 0 solution. So we have 2 cases: consistent system with unique trivial solution, this 0 solution. Then rank of A equal to n, where n is the number of variables. The system is consistent and has only the 0 solution, the unique solution. If the matrix is square matrix, that is m equal to n, and for unique trivial 0 solutions, rank of A equal to n, that means determinant A for this square matrix, determinant A not equal to 0. And consistent system with infinitely many solutions, non-trivial solutions including 0 solutions. If rank of A less than n, then the system is consistent and has this non-trivial solution including the 0 solution if determinant A equal to 0 for this square matrix. Next question, 6c. What is the value of k, the plane x plus y plus z equal to 2, 3x plus y minus 2z equal to k, 2x plus 4y plus 7z equal to k plus 2 intersect in a line, find the equation of the line in that case. Now the given system is this. The augmented matrix, this is the coefficient matrix, and this column is the right hand side constant terms. Now we want to reduce the matrix, this following row operation, this 1 1 1, so corresponding first column, this place is 0 and this place is 0. So the operation is this R2 equal to R2 minus 3 R1 and R3 equal to R3 minus 2 R1. We get this position 0, this position 0, and next we perform this operation R3, new R3 equal to old R3, R3 plus old R2, and this by this operation we get 0 and 0 in this position. Clearly, for this coefficient matrix, the two non-zero rows, so only 1 0 rows for this coefficient matrix A. So rank of A equal to 2. Now, rank of AB, these three lines intersect in line, so system must have infinitely many solutions. So rank of A equal to 2. So rank of augmented matrix must be equal to 2. Otherwise, system cannot have a solution, inconsistent. If this 0, 2k minus 8 is 0, not equal to 0, then system is inconsistent. Then rank of A equal to 2 and rank of augmented matrix is 3, not equal, so inconsistent. Because the system have infinite many solutions intersect in a line, and this line and every point on this line is solution of this system. So this 2k minus 8 must be 0. So k equal to 4. Now I want to find the equation of the line. K equal to 4, back into the row reduced equivalent form of the augmented matrix. So put here k equal to 4 here. So 4 minus 6 is 2, 2 4 8, 8 minus 8 is 0. And so the system reduces to this x plus y plus z equal to 2, and this minus 2y minus 5z equal to minus 2, and minus cancel from the both sides this. Now we can express these variables in terms of the parameter, this let z is equal to t, put here z equal to t. So 2y from the second equation, 2y, y equal to 1 minus 5t by 2. And from the first equation, this put z equal to t and y equal to 1 minus 5t by 2. We get x equal to 1 plus 3t by 2. So the parametric form of the line of intersection is given by x equal to this, y equal to this, and z equal to t for any real t. Now setting all expressions for t equal, so find t here and t here and t here. So x minus 1 divided by 3 by 2, y minus 1 divided by minus 5 by 2, and z by 1. This equals to t. Actually, this equals to t. Next, so multiplying by 2, actually dividing by 2, actually here in the denominator multiplying denominator by 2. So this 3, this minus 5, this 2, and this is the equation of the line in symmetrical form, passing through the point 1 1 0 and parallel to the vectors 3i cap minus 5j cap plus 2k cap. Actually this is the direction ratios 3 minus 5 2. Next question, use elementary row operation to find the inverse of the matrix is this. This is the A matrix, the given matrix, and this I is the identity matrix of order 3. Now we to find inverse, so this augmented matrix AI we reduce to this IA inverse. So this left hand side equal to the identity matrix. First we operation, give the operation this R1, new R1 equal to old R1 by 2 to get the element 1 in the 1 1 position. So this and this position, first column below the leading one, this position 0. So we next operation, we give the next operation is R2 equal to R2 minus 4R1 and R3 equal to R3 minus 6R1. So we get this next position, this 3 to get 1 in this position, we divide the second row by 3. So R2 equal to R2 by 3, this old R2 by 3, and we get this. And to get 0 in this position 4, so R3 old R3 minus 4 R2, we get this one, and this is the identity matrix. Hence this matrix, right hand side matrix, is this the inverse A inverse of the given matrix A. Next question 6e. Show that the vectors alpha 0 1 0, beta 0 1 1 are linearly independent. Find L alpha beta, linear span of alpha beta. What does L alpha beta represents geometrically? So that L alpha beta gamma equal to R3, where gamma equal to 1 0 0. Now to prove the linear independence of alpha beta, so first we write C1 alpha plus C2 beta equal to null vector 0. We want to find this linear, for linear independence, we must have C1 equal to 0 and C2 equal to 0. So C1 alpha is the 0 1 0, and C2 beta, this 0 1 1, this 0 vector, that is 0 0 0. So after simplification, we get this C1 plus C2 equal to 0 and C2 equal to 0. Hence C1 equal to 0, C2 equal to 0. And this shows that the vector alpha and beta are linearly independent, because from this equation we get the only solution C1 equal to 0 and C2 equal to 0. Now to find the linear span of the alpha beta and its geometrical representation. The linear span of alpha beta, L alpha beta, that is L alpha beta, is the set of all possible linear combinations of alpha and beta. Any vector zeta, xi, any vector xi belongs to the linear span of alpha beta, L of alpha beta, then xi equal to A alpha plus B beta. That is A alpha means 0 1 0 and plus B 1 0 1 1. So we can write 0 comma A plus B comma B, where A and B are scalars. Any vector in linear span of alpha beta is of the form 0 y z, where y z are some combination of A and B. Here y equal to A plus B and z equal to B. In R3 equivalent space R3, two linearly independent vectors are not collinear. That is, they do not lie on the same line or parallel line. So this is the line, first this vector, and this is the do not lie on the same line or parallel line. This is the parallel vector, this parallel vector. So this is the collinear vectors. This vector, collinear vector. Or another vector is this. These two vectors also are in the same line. So these vectors are collinear. And this vector and this vector parallel vector, so they are collinear. So two linearly independent vectors are not collinear. So this vector are not linearly independent. Actually, they are linearly dependent. So for linear independent, the vectors must be, and this vector and this vector. This is the linearly independent vector. Geometrically, the linear span of two non-collinear vectors, this is the non-collinear vectors, this vector and this vector, linearly independent vectors in R3, is a plane, because the plane of the paper, this is the plane of the paper, this vectors lies in the plane of the paper. So linear span by these two vectors is the plane of the paper in the R3 that passes through the origin, because all vectors alpha, beta in the linear algebra, this is the vector, this 1 1 0 0 or 1 1 1. This is the point also vector. This means joining the point origin and this point 1 1 1. So all these are passing through the origin. Since the first component of these all vectors in the linear span of alpha beta is 0, here this 0 yz, 0 comma a plus b comma b. So first component x equal to 0. So x equal to 0. So these points, this is the linear span of this alpha beta. The set of all those points are like this, where the first component, that the x component equal to 0. That means this is the these points lie on the yz plane, yz plane. So linear span here, the linear span of alpha beta is the yz plane, the set of all points on the yz plane. This is the plane where x equal to 0. Now we want to show the L of alpha beta gamma equal to R3, equivalence per R3. To show that this linear span is this alpha beta gamma, we must show these three vectors are linearly independent. So first vector 0 1 0, write it in column 0 1 0. Second vector beta 0 1 1, so 0 1 1. Third vector gamma 1 0 0, this 1 0 0. Let's form a matrix, this A matrix. Now we find the determinant of A. After calculation we get this determinant equal to 1. Since determinant is not equal to 0, the vectors alpha beta gamma are linearly independent. Three linearly independent vectors in three-dimensional space form a basis, that is theorem by theorem, for that space. Therefore, any vector in R3 can be expressed as a linear combination of alpha beta gamma. This means that the linear span is the interspace R3. So L alpha beta gamma equal to the interspace R3. Next question 6F. Check whether 0, 12, 20 can be expressed as a linear combination of 1, 2, 3, 2, 4, 6 and minus 1, 3, 7. Using the result, check the solvability of the following system of equation. Now, this vector 0, 12 and 20 can be expressed as a linear combination of V1, V2 and V3. Then we need to determine the scalar C1, C2, C3 such that C1 V1 plus C2 V2 plus C3 V3 equal to 0, 12, 20. So after simplification we get this corresponding component. First, from the first component C1 plus 2C2 plus minus C3 equal to 0. From the second component 2C1 plus 4C2 plus 3C3 equal to 12. And from the third component we get this equation 3. Now from the second equation, taking common 2 from the left hand side, so we get C1 plus 2C2 minus C3 equal to 6. But from the first equation, C1 plus 2C2 minus C3 equal to 0. So from the 2 we get this expression equal to 6. From the equation 1 we get this is 0. Same expression, C1 plus C2 equal to C3. First this equal to 6 and then from 1 is this equal to 0. So this is absurd. This contradicts the one. So the above system given by 1, 2 and 3 is inconsistent. That is, there is no solution for this system. Hence, the vector 0, 12, 20 cannot be expressed as a linear combination of the given three vectors. We cannot get any solution for this system. Second part, check the solvability using this. Check the solvability of this system equation. Actually, this given system same as identical as this equation 1, equation 2 and equation 3. So already we have seen that this system is inconsistent, that is no solutions, not solvable. So obviously this system is also inconsistent also. Next, note that clearly here V2 is equal to 2V1 because 2, 4, 6 is V2, taking common 2, so this 1, 2, 3. So this is the V1, 1, 2, 3. So actually V2 equal to 2V1. So the scalar multiple V2 is the scalar multiple of V1. This means that V1 and V2 are linearly dependent. So we can write this equation C1 V1 plus C2 V2. We write here 2 V1 in place of V2 plus C3 V3. This is equal to C1 plus 2 C1 V1 plus C3 V3 equal to 0, 12, 20. This shows that actually we are looking for a linear combination only two linearly independent vectors. Here V1 and V3 are linearly independent vectors. But we can easily verify that this vector 0, 12, 20 cannot also be expressed as a linear combination of this V1 and V3. And because geometrical explanation for this reason, any arbitrary vector cannot necessarily be expressed as a linear combination of a set of three linearly dependent vectors. So any vectors can be, any vector, any arbitrary vector can be expressed as a linear combination of a set of three linearly dependent vectors. If three vectors are linearly dependent, they all lie within a plane or along a line passing through the origin. Three set of vectors dependent. So one vector, at least one vector of these three vectors must be redundant. So there are two vectors, linearly independent vectors. By these two vectors, we get a plane. We get a plane. If two vectors are linearly dependent, there is only one vector, and this is the only line, single line. So linear dependence of that set of vectors means that one of the three vectors is redundant and this lie on a plane. These three vector linearly dependent vectors, they are all lie within a plane. The ability to express any arbitrary vector depends on whether the set of vectors span the entire vector space in which the arbitrary vector resides. Any arbitrary vector, we can express any arbitrary vector by the three given vectors, that whether this given vector reside on the space generated by this given set of vectors. Any linear combination of these three linearly dependent vectors will also always stay within the same plane or along a line passing through the origin. This is the linear span. Actually, this plane is the linear span by the given set of three vectors. Although one vector is redundant, because the linearly dependent vectors are confined to a lower dimensional structure, a plane, a line. Actually, vectors is three-dimensional space, but here this linear span of this is the lower dimensional structure. We cannot reach every arbitrary vector in the whole three-dimensional space. Only vectors that happen to lie within that specific subspace, the plane or line only, can be reached. Then we can express the vector as a linear combination of the subset of the linearly independent vectors from the given set of linearly dependent vectors. Consider this example. Three linearly dependent vectors, this 1 0 0 0 1 0 1 1 0. This 1 1 0, actually this 1 1 0 equal to 1 0 0 plus 0 1 0. So these three vectors are linearly dependent vectors, and so this vector 1 1 0 is redundant, and then by this vector 1 0 0 and 0 1 0, actually this vector is the joining the point origin and the x-axis at a distance unit length, and this point lying on the y-axis joining the origin and a point on the y-axis at a distance unit distance, these vectors. So these three vectors are linearly dependent because this equal to this their span is 2D xy plane. By these vectors, this 1 0 0 and 0 1 0, we get vectors this, actually this I cap and this from this j cap by this vector, this I cap vector and this j cap vector. So we get through this vector we get plane xy plane, and this plane, on this plane, is the linear span by these two vectors. So any vector lying in the xy plane can be expressed as a linear combination of this, but outside on the xy plane cannot be linear combination of these two vectors. Say suppose this 0, 0, 1, this is the point vector lying on the z-axis, point on the outside of the plane, cannot be expressed xy plane, outside of the xy plane, the lying on the z-axis, this point is lying on the z-axis, cannot be expressed as a linear combination of these three vectors, because all their linear combination will still lie in the xy plane. So this point 0, 0, 1 cannot be expressed as a linear combination of 1, 0, 0 and 0, 1, 0, because this point does not lie on the xy plane. XY plane is the linear span of the vectors generated by this 1, 0, 0, 0, 1, 0. But 2, 3, 0, this point equal to 2 into this 1, 0, 0 plus 3 into 0, 1, 0 can be expressed as a linear combination of 1, 0, 0 and 0, 1, 0. Here 2, 3, 0 lie on the xy plane, which is the span by the set of vectors 1, 0, 0 and 0, 1, 0. Thank you for watching this video.